Good afternoon. So, we are continuing with the different criteria functions which are used for designing of the linear discriminator. So far we have discussed about three types of criteria functions. The first one was the Perceptron criteria, then we have talked about the relaxation criteria, and the last one we have said was the minimum squared error criteria. So, what I have seen in case of perceptron criteria is that you define a criteria function which is given by J p, which is nothing but minus A transpose y for all y which are misclassified. So, this was the perceptron criteria function. And our aim was that we wanted to find out the weight vector A which will actually classify all the training samples properly. Okay. So, when all the training samples are classified properly, in that case this criteria function, the perceptron criteria function J p has to be equal to 0, which is the minimum value, and if any sample is misclassified by the weight vector A, then the criteria function J p will be greater than 0. Okay. And following this, what we have done is we have taken the gradient of this criteria function J p with respect to A, and then we have followed the gradient descent procedure to come to a particular solution, to come to the solution of the weight vector A. And accordingly, we had the weight updation rule or the perceptron algorithm, which was given like this, that A 0 was initially selected arbitrarily, and then in every iteration A k plus 1 was obtained from the previous value A k following the gradient descent procedure, and it was simply A k plus eta times summation of y for all y which are misclassified. And there we have seen the problem with this algorithm is that because we have to take the summation of all the misclassified samples. So, the amount of memory which is required for execution of this particular algorithm is quite high. So, we had a sequential version of this algorithm, where the first step, that is selecting A 0 arbitrarily, remains the same, and what you are doing is you are taking the samples one by one, and whenever a sample is misclassified, instead of trying to aggregate all the misclassified samples together, whenever a sample is misclassified, immediately you go for updation of the weight vector A. So, accordingly, our weight updation rule was sample by sample. So, if the kth sample is misclassified, then immediately you update the weight vector following this updation rule, that is A k plus 1 will be A k plus eta times y k, where this y k is the sample which is misclassified by the weight vector A k, and eta we said that this is the convergence factor. Okay. Similarly, we have also talked about the relaxation procedure or the relaxation criteria. Where the problem faced with the perceptron criteria, that is, we can have a solution vector which is just on the boundary. Okay. So, if you get a solution vector which is just on the boundary, then it is quite likely that if I use that vector for classification of unknown samples, then the probability of misclassification or the probability of error will be quite high. So, what we want is that weight vector should be well within the solution region. Okay. So, that problem is solved by this perceptron criteria, by this relaxation criteria, and in the relaxation criteria, the criteria function was modified as J r A, which is half of A transpose y minus B square upon modulus of y square. Again here this vector y is misclassified. So, it has to be done for all y misclassified. Okay. But our design rule remained the same, that is you take the gradient of this with respect to A and then follow the gradient descent procedure starting from some initial weight vector which is chosen arbitrarily. And so, we have this algorithm, relaxation algorithm, which is given as A 0 is chosen arbitrary and then we have this iterative approach, that is A k plus 1 will be given by A k plus eta times summation of B minus A k transpose y upon mod of y square into y for all y misclassified. And then we have seen that the corresponding sequential version, where the updation rule is modified as A k plus 1 is equal to A k plus eta times B minus A k transpose y k upon mod of y k square into y k, where y k is the sample which is misclassified by the weight vector A k. Okay. And then we have said that both these criteria functions, whether it is Perceptron criteria or the relaxation criteria, these are useful when the samples are linearly separable or the classes are linearly separable, in the sense that given the set of training samples from two classes, say omega 1 and omega 2, I should be able to draw a boundary between these two classes, where this boundary is a linear boundary. So, in case of 2 dimension, it has to be a straight line. In case of 3 dimension, it has to be a plane. For multi dimensions, it has to be hyperplane. So, it is actually a linear boundary between the two classes omega 1 and omega 2. But if the classes are not linearly separable, then neither the Perceptron criteria based algorithm nor the relaxation criteria based algorithm, they will give you a unique solution, and the algorithm will never converge. So, in such case, we have this minimum squared error algorithm or MSE criteria function, where the criteria function is based on an error measure, where error is nothing but y a minus b, where y is the collection of all the training samples. Okay. A is the weight vector and b is called a margin vector. Okay. So, for this MSE criteria, the aim is to reduce square of this error or to minimize the square of this error. Okay. So, accordingly, you define the squared error criteria, which is given by J s as a function of A, which is nothing but mod of y a minus b squared, and I can expand it as A transpose y I minus b I square of this, take the summation over all the samples I is equal to 1 to n if I have n number of training samples. Okay. And then again, if I take the gradient descent procedure or going for that pseudo inverse concept, I get a solution which is given by A is equal to y plus b, where this y plus is actually pseudo inverse of y. Okay. And then we have said that we can still have an iterative algorithm following the gradient descent procedure, and in which case the iterative algorithm will be similar to the algorithms that we have said earlier, that is perceptron criteria or relaxation criteria. Here again our initial weight vector a 0, this will be chosen arbitrarily, and in every iteration step a will be modified as a k plus 1 is equal to a k minus eta times y transpose y a k minus b. Okay. But still you find that here we are considering all the samples together to find out the solution vector. So, again the problem of memory and working with large matrices. So, we can also have in the same manner a sequential version of this iterative algorithm, and in the sequential version of the iterative algorithm, the iteration step will be modified as a k plus 1 is equal to a k plus eta times b k minus a k transpose y k into y k. Okay. So, you find that we can go for a sequential algorithm from this updation state, from this updation step, which actually considers all the samples together. Okay. Now, again this iterative algorithm or the mean square error criteria function based iterative algorithm to find out a solution vector is problematic in the sense that we have said that the perceptron criteria and the relaxation criteria are useful when the classes are linearly separable. If the classes are not linearly separable, in that case we can go for this minimum squared error based criteria function. But if I have a problem where the classes are actually linearly separable, but because we do not know beforehand whether the classes are linearly separable or not. So, a safest approach will be that you go for minimum squared error criteria based criteria function based approach to get your solution vector A. But the problem here is, even if the classes are linearly separable, it is not guaranteed that linear this minimum squared error based criteria function based algorithm will give you an weight vector which will linearly separate the two classes, or it is not guaranteed that I will have a linear boundary between the two classes, okay, where the samples from two different classes will be put into two different regions. Okay. So, I can have a situation something like this, that even if I have the samples belonging to two classes which are given like this, suppose this is a set of samples which actually belongs to say class omega 1, and I can have a set of samples over here. Let me use different symbol, something like this, where these samples actually belong to class omega 2. Okay. Now, here you find that I can easily, so these are my two features x 1 and x 2. So, I have a two dimensional feature vector. Now, here you find that it is quite easy to find out that I can have a line separating these two classes. Okay. So, because these are linearly separable, so I should get an weight vector which will actually define this line. But when I go for this mean square error based criteria function, I may land up with a boundary something like this. Okay. Because in case of mean square error based criteria function, it tries to minimize the sum of squared distances of the different feature vectors from the line. Okay. So, as a result, the boundary that you get, that may not separate the samples belonging to two different classes. Okay. So, how do we solve this particular problem? So, though this MSE or minimum squared error based criteria function may lead to this kind of problem, however, it can be shown that if the classes are really linearly separable, then it is possible to have some A, weight vector A, and some weight vector B, where y A minus B or y A will be is equal to B, where this B is greater than 0. Okay. We did not have any such constant when we talked about the minimum squared error criteria function. Okay. So, if the classes are actually linearly separable, in that case it is possible to have an weight vector A and a margin vector B, where this equation will be satisfied, that is y A is equal to B, where B is greater than 0. So, when I say B is greater than 0, that means every component of B is greater than 0, okay, because B is a margin vector. So, you say that every component, and this will have n number of components if I have n number of samples. Okay. So, when I say this margin vector B is greater than 0, then every component of this margin vector is greater than 0. And assuming this, we have to define a criteria function. Earlier we have defined the criteria function as a function of only the weight vector A, because our aim was to select the weight vector. But now what we have to do is we have to select both A and B, because we do not know that which particular B will satisfy this equation for a particular A. So, we have to try to update or iterate on both A and B. Okay. So, again we have to start with an initial value of A and initial value of B. Okay. Then we have to update on B, and for every updated value of B or for every iterated value of B, we can find out what is the corresponding A. Okay. So, while doing that, when we update B, we have to keep in mind that in none of the cases any component of B can be less than 0. We always have to maintain that every component of B will be greater than 0. And that can be satisfied if we start with a B with every component positive, and while updation, while modification of B, we will allow only a component of B to be incremented, not to be reduced, because if we allow a component of B to be reduced, then there is a possibility that a component of B may come down below 0, okay, which will not satisfy this condition. So, while updation, we have to keep in mind that we will always allow increment of B, but we will not allow reduction of B. Yeah, because that is a matter of scale factor. I have y A is equal to B. Okay. So, what I am saying is I will always increment the value of B, I will not reduce the value of B, because reduction of value of B may lead to a condition that a component of B, say B I, may be less than 0. So, this is what I will not permit. I will always increment the value of B. Okay. And the scale factor that is incorporated, that will be reflected in the corresponding value of A in the weight vector. Is that okay? So, when I do that, I will redefine my criteria function, that is J s. Earlier it was defined as a function of only A. Now, I have to define this as a function of both A and B, where A is the weight vector and B is the margin vector. Okay. However, the definition will remain the same, that J s A B, which is y A minus B square. Okay. Fixed, that was fixed. In MSE algorithm, our assumption was that the margin vector is fixed, and for a given margin vector, we were trying to find out a value of weight vector. Okay. So, the problem that we faced, that whenever we fix the margin vector, because we never ensured that this condition will be satisfied. So, accordingly, we could have got a boundary something like this. It is still a linear boundary. So, this boundary ensures that your sum of squared error will be minimum, but this does not ensure that the classes are actually linearly separated. Okay. So, if the classes are linearly separable, then we have said that we can have a solution of this form, y A is equal to B, where B is greater than 0. Okay. So, we will take the different margin vectors which are greater than 0, and then find out the corresponding value of A. Okay. So, while doing so, we start with an initial margin vector and then go on updating the margin vector with the aim to come to a proper solution. Okay. So, this is what we have. This is our criteria function, squared error criteria function, which is given by J S A B is equal to y A minus B, take the square of the modulus of this error. Okay. Then this error function, we have to take the gradient once with respect to A and then with respect to B, because we want to update both. Okay. So, if I take the gradient of this J S with respect to A, okay, the solution, the gradient with respect to A is what we have seen earlier, that 2 y transpose into y A minus B. Okay. This is what we have seen earlier. And if I take the gradient with respect to B, then the gradient with respect to B is minus 2 y A minus B. Okay. Now, once we obtain any value of B, then the corresponding value of A can be obtained as, so for any B, the corresponding weight vector A can be obtained as y pseudo inverse B, or we can go in for the same iteration which we have done when we discussed about the mean square error algorithm. Okay. If we are not sure that this pseudo inverse is non singular, because if the pseudo inverse is singular, we cannot have if y transpose y inverse is singular, then we cannot compute the pseudo inverse. Okay. So, for computation of A, either we can go for this if we are sure that y transpose y inverse is not singular, or we can employ the same iterative algorithm that we have discussed earlier. Okay. So, here our main aim is that we have to find out a proper value of B by following the gradient descent procedure with the help of the gradient of J S with respect to B. Okay. And while doing so, as we said that we have to ensure that none of the components of B can fall below 0, and that is what we said, that we can only allow increment of the components of B. We cannot allow reduction of the components of B. So, if I want to do that, in that case, at every iteration I can have B k plus 1, which is same as the same gradient descent procedure B k minus eta times, that is rate of convergence, half of gradient of J s with respect to B minus modulus of gradient of J s with respect to B. Okay. So, here you find that because to obtain B k plus 1, we are subtracting from B k this quantity. Okay. So, if gradient of J s with respect to B is positive, then what we are ensuring is that this total quantity will be equal to 0. Okay. Whereas, if gradient of J s with respect to B is negative, okay, so here it is minus, here it is also minus. So, I get a negative quantity which is twice of gradient of J s with respect to B. So, to nullify this factor 2, you incorporate this half, okay, and here it is negative, here also it is negative. So, overall you get a positive term. So, effectively what I am doing is to obtain B k plus 1 from B k, to B k I am adding a quantity. Okay. I am not subtracting any quantity from B k to get B k plus 1. So, that ensures that your B k plus 1 can be at most greater than B k. It can never be less than B k. Okay. So, by this step we are ensuring that none of the elements of the margin vector B will be reduced at any step of iteration. And since we are ensuring that it will not be reduced in any steps of iteration, so the possibility of having a component of margin vector B which is less than 0 will not arise. Okay. So, our iteration algorithm on B will be same as before, that we will have a B 0 greater than 0, but otherwise arbitrary. Okay.
Sir, here grad B JS modulus, is it a scalar or vector?
Gradient of,
Is it the modulus, is it the magnitude of the gradient vector?
it is magnitude of every component of the gradient vector. What I am saying is every component, it is not modulus.
So, it is a vector.
It is a vector. It is a vector only with the positive components.
So,
okay.
the vector is minus B1, then minus B2, B3.
Yeah,
then
it will be
plus B1,
plus B2, B3.
then B3.
Yeah. Is that okay? So, the iterative algorithm will be something like this, that B 0 will be greater than 0, which is initially chosen, but otherwise it is arbitrary. Okay. And at every step, this B k plus 1 will be B k minus eta times half gradient of B j s minus modulus of gradient j s with respect to B. Okay. So, once I have a particular value of B, I can use that B to compute the value of A, either making use of the pseudo inverse or following the another iterative algorithm for obtaining A by using the gradient descent procedure with gradient of J s with respect to A. That is similar to what we have discussed in our last class. Okay. And by doing this, because we are ensuring that B will always remain greater than 0. So, it is quite likely that even for linearly separable cases, we will get a solution vector which will actually linearly separate between the two sets of samples belonging to two different classes. Okay. Now, all these different criteria functions that we have discussed so far, whether it is perceptron criteria or relaxation criteria or this minimum squared error criteria, in all these cases we have assumed that we have just two different classes, omega 1 and omega 2. Okay. And our criteria was that if A transpose y is greater than 0, the sample belongs to one class. If it is less than 0, it belongs to another class, or if A transpose y is greater than B, it belongs to one class. If A transpose y is less than B, it belongs to another class. Right. Now, the question is how to generalize this in a multi-category case, because in all practical situations we will have multiple number of classes, not that we will have only two classes. Okay. And that is what is the essence of a linear machine that we have said earlier. That is, for every class omega I, okay, we have a discriminant function defined as j I x, okay, where this j I x is nothing but w I transpose x plus w I naught. Sorry. Okay. So, this is the linear equation or the linear discriminant function for every class I, right. So, for given any unknown sample x, I have to compute this discriminant function for all values of I varying from 1 to c, if c is the number of classes. Then for whichever I g I x is maximum, we have to assign or you have to classify x to that particular class. Okay. So, we have something like this, that we have this g 1 G 2 like this. If there are C number of classes, we have this discriminant function G C, then given a vector x, the vector x will be fed to the discriminant functions of all the classes. Okay. Then I have a max selector. Okay. All these outputs come to this max selector, and then max selector, depending upon whichever discriminant function gives you the maximum value, this gives you the class identification. Right. And this is what we have said, it is a linear machine. Okay. And we have seen earlier that following the Bayes decision theory, if I know what is the parametric form of the probability density functions of the samples belonging to different classes, then following Bayes minimum error rate classification or minimum risk classification, we can obtain the classifiers or we can obtain the discriminant functions for different classes. Okay. And there we have discussed about the different situations when this discriminant function can be a linear discriminant function, or when this discriminant function will be a quadratic discriminant function, right. But now we are talking about the non-parametric cases, that is, we do not know that what is the probability density function of the samples belonging to different classes. So, whether it is possible to have algorithms like these gradient descent procedures to have this sort of linear machine which can classify and sample to one of the C different classes. Okay. So, here we find that our condition is something like this, that if I get that G I x, okay, where x is the sample vector, G I x is the discriminant function corresponding to the class omega I. Okay. So, if G I x is greater than G j x, okay, for all j not equal to I. Okay. So, if G I x is greater than G j x for all j not equal to I, this indicates that x belongs to class omega I, because G I x is maximum among all the discriminant functions. Okay. So, this indicates that the sample x belongs to class omega I, right. Or in other words, if I expand this, it simply becomes A I transpose y, okay, where this y is the augmented vector x by adding 1 to it. Okay. So, A I transpose y is greater than A j transpose y, okay, again for all j not equal to I. So, that is the condition that this sample x or sample y, augmented sample y, that belongs to class omega I. Okay. And since we are having C number of classes, that is I and j, that can vary from 1 to C. So, you find that for a particular value of I, when I have this condition that j is not equal to I for all values of j. Okay. So, this j will assume every value from 1 to C except I. That means, j can have C minus 1 number of values. Okay. So, that one which is left out, that is equal to I. So, this inequality, that A I transpose y greater than A j transpose y for all j not equal to I, this is actually equivalent to C minus 1 number of inequalities. Is that okay? So, in all those inequalities, I have to have this particular condition true, that suppose I is equal to 1. Okay. Say A 1 transpose y must be greater than A 2 transpose y, A 1 transpose y must be greater than A 3 transpose y, A 1 transpose y must be greater than A 4 transpose y, and so on up to A transpose y must be greater than A c transpose y. Then only I can say that this sample y or the corresponding sample x that belongs to class omega 1. Okay. So, this equation actually corresponds to, for all values of j, c minus 1 number of inequalities. Okay. So, whether it is possible to have an unified approach to take care of this c minus 1 number of inequalities simultaneously and give me c number of weight vectors A 1, A 2, A 3, A 4 up to A c. Okay. So, over here you find that, let us take a specific case that I is equal to 1. Okay. So, I want that A 1 transpose y must be greater than A j transpose y, okay, for y varying from 2, 3 up to c minus 1. Okay. Later on we will generalize. So, I take a particular value of I which is equal to 1. Okay. So, we find that all these c minus 1 number of inequalities can be put in an unified approach if I take a c into d hat dimensional weight vector.
Total number of equalities should be C.
C minus 1, C minus 1.
Sorry, C minus 1.
Yeah.
But here it is 2 to C minus 1. That means total number of equalities.
Sorry, 2 to C, right. It is 2 to C, not C minus 1. Total number of inequalities is C minus 1. Okay. So, all these inequalities can be put in an unified form in a single expression if I consider a C d hat dimensional weight vector. Okay. I am taking the same terminology which we used earlier, that my weight vector is actually d dimensional. Okay. So, after appending 1, it becomes d plus 1 dimensional. So, that d plus 1 we are taking as d hat. Okay. So, I take a d c into d hat dimensional weight vector. Let us say this weight vector is alpha. Okay. Now, what is this alpha? This alpha will be nothing but A 1, A 2, A 3 up to A c. This is my weight vector alpha. Each of these weight vectors A 1, A 2, A 3 up to A c, each of them are actually d hat dimensional. Okay. I have c number of such weight vectors. So, that overall dimension of this vector alpha is c into d hat.
Sir, is it y equal to 2, 3, c or j?
Thank you. J equal to 2 to c. Okay. So, this overall vector that becomes c into d hat dimensional. Okay. So, we can think that this particular weight vector, if I have this condition that A 1 transpose y greater than A j transpose y for all values of j varying from 2 to c. Okay. So, I can equivalently say that effectively this c into d hat dimensional weight vector alpha will properly classify all the c minus 1 number of feature vectors, where the feature vectors will be of the form, say let me put it as eta 1 2, which is nothing but y minus y 0 0 0 eta 1 3 will be y 0 minus y 0 0 0 . It will continue like this, eta 1 c will be is equal to y 0 0 0 minus y. Okay. What this 0 actually means that this is a column vector of dimension d hat. Okay. Y is obviously a column vector of dimension d hat, minus 1 y is also a column vector of dimension d hat, 0 is also a column vector of dimension d hat, where every component is equal to 0. Okay. So, as there are c number of such vectors, every vector having a dimensionality of d hat. Okay. So, the overall dimension of these vectors eta 1 2 or eta 1 3 up to eta 1 c, each of them are of dimension c into d hat. Is that okay? So, this inequality, that A 1 transpose y greater than A j transpose y for j varying from 2 to c, okay, it is equivalent to saying that alpha transpose eta 1 2 is greater than 0, is it not? If I put these two side by side, okay. So, let us take these two vectors side by side. Alpha is y a 1 a 2 a 3 up to a c, eta 1 2 is y minus y, then all components are 0. So, if I take alpha transpose eta 1 2, okay, that computation will be equivalent to a 1 transpose y minus a 2 transpose y. Okay. Rest of the components in eta 1 2 are 0. So, that corresponding vector multiplication will have null effect, will not have any effect on the result. Is that okay? So, if I take alpha transpose eta 1 2, that is simply a 1 transpose y minus a 2 transpose y, right. Similarly, alpha transpose eta 1 3, that will be simply a 1 transpose y minus a 3 transpose y. Is that okay? Similarly, alpha transpose eta 1 c, it will be simply a 1 transpose y minus a c transpose y. Okay. So, this condition that a 1 transpose y greater than a j transpose y or a 1 transpose y minus a j transpose y greater than 0 for all the values of j, for y to be classified to class omega 1, that is equivalent to saying that this weight vector alpha properly classifies all these c minus 1 number of feature vectors, okay, where these feature vectors are actually generated from the original feature vector y. So, you find that the overall data that we are generating over here, that increases dramatically, and that is quite obvious, because from a 2 dimension, from a 2 category case, we are moving to C category case. So, your computation obviously will be C-fold. Okay. So, for every feature vector y, I am generating C minus 1 number of feature vectors, right, where the dimensionality of the feature vector, each of these feature vectors is also being incremented by a factor C. Okay. Initially, vector y is of dimensional d hat. Now, each of them are of dimension C into t hat. Okay. So, the dimensionality is increasing by the number of classes that we have, and the number of vectors for every original vector is also being increased by a factor c into c minus 1. Okay. So, the amount of data that we are generating, that becomes quite high. Okay. So, this is what we have considered for a particular case by assuming I is equal to 1. Okay. In general, a feature vector eta I j will be something like this, that I will have these vectors having components 0, ith component will be equal to y, jth component will be minus y, then followed by zeros again. Okay, where this is my ith component and this is my jth component. Is that okay? And this alpha transpose eta I j greater than 0, that is equivalent to, if you follow from here, it will simply be A I transpose y minus A j transpose y, that will be greater than 0. Okay. So, if this condition is satisfied for all values of j not is equal to I, then we say that the sample y actually belongs to class omega I, it does not belong to class omega j. Okay. So, when I have this sort of formulation, that alpha transpose eta I j, okay, for every such inequality, I actually have the weight vectors corresponding to discriminant functions of two different classes omega I and omega j involved in it. Okay. And for proper classification of any sample y, I must have that it alpha transpose eta I j must be greater than 0. That means, A I transpose y minus A j transpose y must be greater than 0. Okay. So, if I find that this condition is not satisfied for any value of y, for any sample y, then I have to modify actually two weight vectors. Not only A I also have to modify A j, okay, because both of them are responsible. In earlier case, because it was a 2 class problem, so I had a single weight vector. So, I have to decide whether to modify that weight vector. If it is to be modified, in which way it has to be modified. Okay. Now, I have two weight vectors involved, one for the discriminant function of class omega I and the other one for the discriminant function of class omega j. So, anytime any sample is misclassified by alpha, I have to modify both these weight vectors A I and A j, okay, involved in that particular eta I j. So, the weight updation or weight vector updation rule in this case can be simply like this. Initially, I assume that A I 0 is arbitrary for all I. Okay. That means, for every class, I assume an arbitrary weight vector initially, right, and then for any vector which is misclassified. So, with the help of this initial weight vector, I have to form initial alpha, okay, which is just concatenation of all these different weight vectors. Using that, I have to go for classification of the samples, or the samples are to be modified in this form. Okay. Whenever I know that a sample belongs to class omega I, so for every such I have to generate eta I j, where the ith component will be equal to y and the jth component will be minus y. So, I have to generate eta I 1, I have to generate eta I 2, I have to generate eta I 3, I have to generate up to eta I c. So, for each of these samples, I have to generate c minus 1 number of sample vectors, okay, and I have to make I have to ensure that each of those modified sample vectors are properly classified by the corresponding alpha. If any of those samples is not properly classified by alpha, then I have to modify both A I as well as A j. Okay. So, that weight updation rule will be A I k plus 1 will be is equal to A I k plus y k, where this is the sample which is misclassified. Okay. And this is what we have obtained using our perceptron criteria earlier. Okay. This expression is same. So, we are incrementing A I in a particular direction, A j has to be incremented in the negative direction, because we want to penalize A j, okay, whereas we want to reward A I. Okay. And A j k plus 1, for this the weight updation rule will be, this will be simply A j k minus y k. Okay. So, you find that only two weight vectors we are updating, one is A I and A j, okay, for every eta I j which is misclassified. Okay. And all other weight vectors will say that A L k plus 1 will remain as A L k, where L is not equal to I and L is not equal to j. Okay. So, only the ith weight vector and the jth weight vector, these two we are modifying. Okay. Modification of ith vector follows the same updation rule that we have obtained in the perceptron criteria. Okay. Modification of the jth weight vector A j, similar updation rule, but instead of incrementing we are decrementing it. Okay. So, A I is actually rewarded, A j is penalized. All other weight vectors other than A I and A j, they remain unchanged, because these weight vectors really does not take part to tell us whether alpha transpose eta I j is greater than 0 or not. Okay. These weight vectors do not tell us anything about this. Only the weight vectors A I and A j decide whether this condition will be satisfied or not. Is that okay? So, we are keeping A L k plus 1 is equal to A L k for all values of L which is not equal to I and not equal to j. Okay. And this kind of construction, because you find that every time from A I we are constructing this weight vector alpha, okay, and for every sample y we are constructing alpha eta I j. Okay. This kind of construction is what is known as Kesler's construction.
So for every iteration we are penalizing this j,
Yeah.
and we are crediting this
Yeah.
I. One is sufficient. We can credit one thing and
Yeah, one is sufficient, but there is nothing wrong if you do both of them together. Okay. Because our aim is that we want to have A I transpose y minus A j transpose y greater than 0. So, you increment one, reduce the other one, so that this condition is reached quite fast. Is that okay? If you do not do this, maybe the number of iterations that will be taken will be more, nothing else. Okay. So, let us stop here today. Thank you. Good morning. So, today we are going to start our discussion on use of neural network for pattern recognition. So far what we have discussed, initially we started discussing about the Bayes decision theory, where we have seen that the classifiers are to be designed using the probability density function of the training samples, and later on we have gone to non-parametric classification techniques, where we have seen the different types of criteria functions like Perceptron criteria, relaxation criteria, or minimum squared error criteria, which are to be designed, which are to be minimized for designing of a linear classifier. So, before I actually go to this use of neural network for pattern recognition, let me briefly tell about two more techniques of non-parametric pattern classification. So, one of the non-parametric technique for pattern classification is called a nearest neighbor rule. Or nearest neighbor classification. Or it is also called NN rule. So, when you use this nearest neighbor classification technique, what you do is instead of trying to design any classifier or any discriminant function for any of the classes, what I have is I have a set of training samples, the training samples coming from different classes. So, if it is a 2 class problem, I will have training samples coming from 2 different classes. For a C class problem, I will have training samples coming from C different classes. In nearest neighbor classification, what we do is whenever an unknown sample is given, we have to classify this unknown sample to one of the classes for which I have the training samples. So, what I simply do is I simply find out the nearest training sample which is nearest to the unknown sample. That means, you try to compute the distances from that unknown sample to on all other training samples which are provided, okay, and you find out the minimum of those distances. So, whichever sample is nearest to the unknown sample or the distance is minimum, I know what is the class belongingness of that particular sample, of that training sample which is nearest to the unknown sample. So, accordingly, you classify this unknown sample to the class of the training sample which is nearest. Okay. So, I have situation like this. So, if I have a set of training samples, so these are the training samples which belong to one class, and suppose these are the training samples that belong to another class. Okay. And suppose I have an unknown sample which is somewhere over here. Okay. So, if these samples actually belong to class omega 1 and these are the samples which belong to class omega 2, okay, I just find out that which sample is nearest to this unknown sample. So, you find that the distance between this sample and this sample is minimum. So, the nearest sample is this one, and this sample belongs to class omega 1. So, I simply classify this unknown sample to class omega 1. Okay. But this particular approach has a problem. The problem in the sense that a sample nearest does not mean that it is most probable class. Okay. So, I can have a situation something like this. So, I put again I take 2 dimensional feature vectors having the feature components x 1 and x 2, okay, and the samples are for one class something like this, and for another class the samples may be something like this. Okay. So, I say that these are the samples, training samples taken from class omega 1 and these are the training samples taken from class omega 2. Okay. And in over here, if the unknown sample is somewhere at this position. Okay. So, you find that as before, this unknown sample will have a minimum distance from this training sample which belong to class omega 2. Okay. So, I will classify this sample to belong to class omega 2. Okay. However, you find that here I have a single point, a single sample from class omega 2. Okay. Whereas, I have more number of samples from class omega 1, okay, which may actually or which should actually influence the classification of this unknown sample. Okay. But without looking at the density of the training samples, we are blindly classifying this unknown sample to a class which is nearest to one of the training samples. Okay. So, this sort of nearest neighbor rule does not take into consideration the maximum probability of a class. Okay. So, a solution to this is that instead of taking a single point which is nearest to the unknown sample, you take a pre-specified number of points which is more than 1. Okay. Then try to classify this unknown sample to one of the classes based on a voting mechanism which is given by those training samples where the number of training samples is pre-specified. Okay. So, accordingly we have a rule which is k nearest neighbor rule. Or KNN classification. So, over here what you do is instead of taking a single point which is nearest to the unknown sample, you take k number of points, k number of training samples which is nearest to the unknown sample. Okay. And these samples, this k number of samples may come from a single class, may come from multiple number of classes. And out of these k nearest neighbors or k nearest training samples that we get, you try to find out that which class is mostly occurring, is maximally occurring in that k number of samples or k number of training samples. So, whichever class is maximally represented in that k number of samples, you classify these unknown samples to that particular class. Okay. So, considering that,
then how will we select this k number of samples from which from omega 1 class or omega 2 class?
it may be from any class. I just want that I have to have k number of samples which are nearest to the unknown sample. I do not bother about whether it belongs to class omega 1 or it belongs to class omega 2. Okay. And once I have that k number of training samples from whichever class it is, without any class consideration, you take k number of training samples which are nearest to the unknown sample. And within that k number of nearest samples, now you find out that from which of the class I have got maximum number of samples, right. So, which class is maximally represented in that k number of samples. So, whichever class is maximally represented in that k number of samples, I classify the unknown sample to that particular class. Okay. So, coming to this same example, so this is the position of the unknown sample, okay, and these are the samples which are from class omega 1, these are the samples from class omega 2, right. So, what I do is I try to incorporate k number of samples which are nearest to this. Okay. So, for doing that, what I have to do is I have to find out the distance of the training samples, whether it is coming from class omega 1 or it is coming from class omega 2. Irrespective of that, I have to find out k number of samples which are nearest to this unknown sample. Okay. So, suppose I decide the value of k is equal to 5. Let us take any value. Okay. So, I will take 5 samples which are nearest to this unknown sample. Obviously, this is nearest to this training sample. So, this will be included in that 5 samples. Among the remaining, suppose these 3 are the samples, or maybe this one. So, these 4 of the other samples which are also nearest to this unknown sample. So, I have selected 5 number of samples. Okay. Out of 5, you find that there are 4 samples which are coming from class omega 1, and I have only 1 sample which is coming from class omega 2. So, it is class omega 1 which is maximally represented in those 5 training samples. Okay. So, I have to classify this unknown sample x to class omega 1 rather than class omega 2. So, you find the difference that if I go for simple nearest neighbor rule, that is, I find out one training sample which is nearest to the unknown sample. In that case, this unknown sample is classified to class omega 2, whereas if I take 5 nearest samples and out of those 5 I find out which class is maximally represented, and here it is class omega 1 which has 4 samples out of the 5, whereas class omega 2 has got only 1 sample out of 5. Okay. So, accordingly, this unknown sample is classified to omega 1 rather than class omega 2. Okay. Now, naturally, if I go for the nearest neighbor classification where value of k is equal to 1, okay, the error rate or the error bound will obviously more than the error bound that you get by using Bayes decision or Bayes minimum error classifier. Because in case of Bayes minimum error classifier, we classify an unknown sample to a class for which the probability of a particular class is maximum. Okay. And in case of a single one NN or nearest neighbor classification rule, I am just taking a sample which is nearest to the unknown sample, and that particular sample, training sample, may be just an offshoot. Okay. I may not have other training samples nearer to this belonging to the same class. So, accordingly, the probability of that particular class in that region is very less. Okay. So, naturally, the error that you get in case of nearest neighbor rule is more than the error that you get using Bayes minimum error classifier. Whereas, if I go for this KNN classification, okay, where I am trying to find out that which class is maximally represented in those k number of training samples, okay, and it can be shown that if value of k as well as value of n by k, where n is the total number of samples, okay, is very large, in that case the error bound of KNN classification approaches the error bound of Bayes minimum risk classification. The reason is very simple, that if k is very large and also n by k is very large, then the number of samples within a small region, that gives you a good approximation of the probability density function of the samples belonging to different classes. Okay. So, in the limit when k becomes very large as well as n by k becomes very large, the error bound given by KNN classifier approaches that of the Bayes minimum error classifier. Okay. Now, following this, if I go for simply nearest neighbor rule, I should be able to find out what is the decision boundary between different classes. Okay. So, let us take a very simple example, something like this. Say I have a number of samples. So, this is one sample, this is one sample, okay. This is one and this is one, and I may have another sample somewhere over here. Okay. And let us assume that this sample belongs to class say omega 1, this sample belongs to class say omega 2, this sample belongs to class omega 3, this one belongs to class omega 4, and say this one belongs to class omega 5. Okay. Now, following nearest neighbor rule, if I want to find out what is the decision boundary which separates all these different classes. Okay. So, you find that whenever I go for nearest neighbor rule, the nearest neighbor classifier is nothing but a minimum distance classifier, okay, because the class to which I am classifying this unknown sample, I have one sample from that class whose distance from the unknown sample is minimum. Okay. So, naturally, this is nothing but a minimum distance classifier. And if I have a minimum distance classifier, then the decision boundary between the two classes, where I have representatives of the two classes, okay, then the decision boundary is nothing but a perpendicular bisector or orthogonal bisector of the line joining those two exemplar samples or those two representatives. Okay. So, following that, you find that the decision boundary between class omega 1 and omega 2 will be an orthogonal bisector of the line joining omega 1 line joining these two samples. Okay. So, the decision boundary that I have is simply this, and it will be extended on this side, okay, as regards omega 1 and omega 2, and it will be extended on this side. Now, coming to the decision boundary between class omega 1 and omega 5, okay, that will also be an orthogonal bisector of the line joining omega 1 and omega 5. Okay. So, this decision boundary will be simply this, right. Similarly, the decision boundary between classes omega 1 and omega 3, that will be orthogonal bisector of this line. So, this particular decision boundary, sorry, it will be something like this, will be this one. Okay. In the same manner, the decision boundary between omega 3 and omega 5 will be this, between omega 5 and omega 4 it will be this, between omega 2 and omega 4 the decision boundary will be this, between omega 3 and omega 4 the decision boundary will be this, and between omega 2 and omega 5 the decision boundary will be like this. Is it okay? So, if I follow the nearest neighbor rule, I can very easily find out the decision boundary among different classes for which I have the training samples. Is it okay? So, these are the different non-parametric techniques for classifier design or for classification of unknown samples to one of the known classes. Okay. So, now let us start our discussion on use of neural network for pattern recognition. Okay. So, when we talk about a neural network is nothing but a computational model which tries to imitate the human brain. Okay. So, when we talk about our human brain or human nervous system, this actually consists of a number of numerous nerve cells. Okay. And in the nerve cell is something like this. If you draw any particular nerve cell, it goes like this, okay, where this whole thing is a cell body. These are what are called dendrites, or sensors. Okay. Inside I have the cell body, okay, and these fibers, these are actually called actions. Okay. So, these dendrites of the sensors, they actually sense different stimulus, okay, and that signal is carried to the brain by these actions. Okay. And depending upon what kind of stimulus or what kind of sensing this cell body has done, the brain takes a particular action, decides an action, and sends that information to our different muscles through a set of such neurons, and then we take certain action by activating the corresponding muscles. Okay. So, when we talk about the neural network also tries to imitate a functionality something like this. Okay. So, a neuron model for machine intelligence or for artificial intelligence will be something like this. Say I have to have something like a cell body, okay, and then I have to have a set of inputs which act as dendrites, okay, and then I have to have an output which will act as the action, right. So, what I have is I give the feature vector as input to this neuron, okay, and our feature vectors are having different components x 1, x 2, x 3 up to say x n, if I have n dimensional feature vector. Okay. Then this cell body performs an weighted summation of these different feature components, okay, and weighted sum is fed as an input to a nonlinear function, and in most of the cases this nonlinear function is some sort of a threshold function, okay, or it may be a continuous nonlinear function as well. Different types of neural networks use different types of nonlinearity, okay, and this is our output. Let us call it as y, okay, and because this will be this particular cell body will compute the weighted summation of these different feature components. So, I have to have the corresponding weights, okay. So, those weights are say W 1, W 2, W 3 and W 4. Okay. So, what I have at the output of this is just like summation of W I x I, where I varies from 1 to n, okay. And on this I have a nonlinear function f, and that is my output y, okay. If I use this nonlinearity as a simple threshold function, then what I will have is, if this nonlinear output, if it is greater than threshold, Okay. I set y to 1, and if this is less than or equal to threshold, I set y to 0. Okay. So, having this kind of functionality, you find that it has a very close similarity with one of the linear discriminators that we have designed earlier. Okay. That is, we have said that if g I x is greater than 0, it belongs to some class, if it is less than 0, it belongs to some other class. And if I have a linear discriminant function, that g I x is nothing but this summation of w I x I varying from 1 to n, where my feature vector is n dimensional. Okay. And if this function is greater than threshold, I set y is equal to 1, indicating that this x belongs to one class. If this is less than or equal to threshold, I set y equal to 0, indicating that this x belongs to the other class. Okay. Earlier we have said that if it is equal to 0, then x actually belongs to the boundary. I can also put that condition over here. If this function weighted sum becomes equal to 0, I will not take any action. Okay. Whereas, if it is less than 0, then only I will set y equal to 0. So, accordingly, this function will be different, or the threshold function will be equal to will be different, where if this weighted sum becomes equal to 0, then I will not take any action. Okay. However, in case of linear discriminant function, we have seen that before you go for designing the classifier, you have to append 1 to the feature vector. So, you get a modified feature vector, and this purpose of this modified feature vector is that I can incorporate a bias weight which are different corresponding to different classes, that is w I 0. Okay. I can also incorporate the same bias within our neural model. What I can do is, I can simply, so let me draw the same neural model, where I have this addition and I have different inputs. Okay. One of the input I can put equal to 1 constantly, and the weight given to this corresponding input can be w naught. Okay. Whereas, to other inputs, I have the different components of the feature vectors, that is x 1, x 2 up to x n. Okay. The other functionalities remain the same. I have this non-linearity, and then I have get this output y. Is it okay? So, over here you find that output of this is summation of x I into w I varying from 1 to n plus w naught. Okay. And on top of that, I put this non-linearity, which gives me the output y. Okay. Again, I can have similar kind of decision that y will be set equal to 1 if this term is greater than threshold, it will be set to 0 if this term is less than or equal to threshold, and accordingly I can go for classification. Okay. So, you find that in both the cases, the model that we have is closely similar to what we have followed in case of linear discriminant function, and we have seen that there are different approaches of designing the linear discriminant function, okay, like Perceptron criteria, relaxation criteria, mean square error criteria, minimum square error criteria, and so on. So, what I have to do whenever I go for designing such a kind of neuron is that I have to select the weights or Wi properly, okay, which was the purpose of having different types of criteria functions. We wanted to have different weight vectors, a weight vector which give you proper classification between two or more classes. Okay. So, here also the major task is to decide about these connection weights, okay, and that is what is done during training or learning of neural network. Okay. And as it is very close to what we have got in case of Perceptron criteria, a neural network formed out of such neuron models, they are also called perceptrons. Okay. So, in the simplest case, I can have a single output single layer perceptron, okay, which is nothing but a single neuron like this. So, in case of a single output single layer perceptron, the neural network is simply this. So, now all this function we put in the form of a node, these two taken together can be represented by a node. So, when I say a node, the node includes both this adder which performs a weighted summation as well as this nonlinear unit. So, a node gives me this particular output for a given input. Okay. So, a single output single layer perceptron is a single node something like this. So, which has a number of inputs and one output. Okay. I can say that, so this is my neural node, or let me not use n, because in many cases we are using n to represent the dimension. Okay. If I have a biased one of the inputs will be equal to 1 and the other inputs will be the different components of the feature vector up to say x m, let us say. Okay. And here my g I x, what this node compute is simply summation of w I x I varying from 0 to m. Okay. And we say that if this is greater than 0, then we say that the vector x belongs to class omega 1. Okay. If this is less than, or let us include equal also, if it is less than or equal to 0, we say that the sample x belongs to class omega 2. Okay. Now, in case of perceptron criteria, we have said that this weight updation rule was that initially we decide w 0 to be arbitrary, okay. When we had the perceptron criteria, initially we decided that w 0, the weight, initial weight is chosen arbitrarily. Then at every iteration stage, the weight was chosen as w k plus 1 was equal to w k plus eta times y. Okay. This is what we had in case of perceptron criteria. Now, similarly, in this case also we have to have some weight updation rule which will update the weights of the input links. Okay. And this weight updation has to be done using the training samples that which are provided. Okay. So, we have to make use of all the training samples which are provided and keep on updating the weights until and unless we get the correct output. Okay. And since the training samples, we know what are the class levels of the training samples, then for a training sample I know what should be the corresponding output. Okay. So, if a training sample x belongs to class omega 1, I know that output should be equal to 1. If the training sample belongs to class omega 2, I know that output of the neuron has to be equal to 0. Okay. So, what I can do is I can find out what is the difference between the target output, if the actual output I call it as target output, that is what is expected. Okay. And because of improper weights, improper connection weights, I may get an output which is not actually the target output. Okay. So, the difference between the target output and the actual output is the error, right. And all the weight updation rules, connection which updates the connection weights in a neural network, tries to minimize that output error, because I know that what is the exact output, what should be my target output and what output I actually get. So, I can compute what is the error, then try to minimize that error by modifying the connection weights. Okay. So, over here you find that for a given input x, for a given training sample x, if I know that my output, the target output is say d. Okay. Whereas, the actual output that I get is nothing but summation of w I x I, where I varies from 0 to m. Okay. So, this is my target output, this is the actual output that I am getting. So, the error E is nothing but d minus d. Okay. I can have sum of squared error from this. So, I can say that sum of squared error, let me write it as capital E, which is nothing but half of summation d. Let me say that this is for a pth sample. So, dp. So, I will have dp where p varies from 1 to capital N, where capital N is the total number of training samples. So, for every sample I will have an error. Okay. Take the summation of that error, summation of square of the error, which gives you the sum of squared error. Okay. Out of this you find that this sum of squared error is actually a function of w, where w is the connection weight, right. So, the simplest approach that can be taken is you try to minimize this by differentiating this with respect to w. Okay. And as w has got m plus 1 number of components. Okay. So, by differentiating this with respect to w and equating that to 0, I will get m plus 1 number of simultaneous linear equations. Okay. You solve that set of simultaneous linear equations, which will give you the values of different components of w. Okay. And you set that different values of w as your connection weights, and your neural network should give you the classification result whenever an unknown sample is fed to the input of the neural network. Okay. However, as we have done in our earlier case, that instead of trying to solve this number of simultaneous equations, we can have sequential algorithms or iterative algorithm, which will iteratively update the weight vector or the connection weights. Okay. And for that, what we have to do is we have to go for gradient descent procedure.
For every x this has to be this, or for all the x's, that the sample is x.
Pardon?
X is the input vector.
X is the input vector.
So, we have such a vectors e equal to 1 to n vectors.
Yeah.
Sir, I think xi should be different for different pattern.
Xi is different for different pattern. Yeah.
So, for that given x xi key, or we are minimizing this error for the given x, or set of x's we are minimizing this error.
You mean to say that I should put it as like this? Does it really matter? Okay. If it is pth sample, yeah. If it is pth sample, I can put it like this also. So, this is the ith component of the pth sample. You can put it like this. Okay. So, we can again follow the gradient descent procedure. For that, we have to take the derivative of this squared error with respect to our weight vector w. Okay. So, if I take the gradient of this, say del E upon say del w I, which is the ith component of the weight vector, where this I varies from 0 to capital M, as there are m number of m plus 1 number of components, including that one that we have added as bias. Okay. So, this del E del w I, if you compute this, it will simply become d minus d into x I. Okay. If you differentiate this with respect to w I, then what I get is this d minus d, d is the actual output that I get. Okay. So, lowercase d is the target output. So, d minus d is the error that I can easily compute into x I. Okay. So, accordingly, our weight updation rule will be w k is equal to w k following that gradient descent procedure minus eta times d minus d into x I. Okay. So, you find the difference between what we had in case of perceptron criteria. In case of perceptron criteria, our weight updation rule was something like this, that w k plus 1 is equal to w k plus eta times y, where y is the vector. Okay. So, the entire weight vector was being modified simultaneously. Okay. And in this case, it is
If we differentiate this with respect to Wi, then I think we will get d minus capital D minus small d summed over all p, and
no, that differentiation you do, it will come this, because we are differentiating with respect to w I, that is the ith component of w. So, jth component, that is w j x j, which is independent of w I, that will become 0. So, I will be left with only x I. Okay. The contribution of this x I into this error term was w I into x I. Okay. So, what is this differentiation? Del E del w I is nothing but, if I expand this whole term, because this is square, I will have 2 into this into del w I of d p minus d p.
So, sir, this
Summation.
differentiation is for pth sample, and for pth sample
I am not,
weight.
for the time being, I am not considering pth sample. Given a particular sample, what is the error? Okay. So, given a sample, the error is d minus d.
So, in that above equation, there is a given that it
This is
pth.
pth sample, this is for individual samples. This is for individual samples. I am trying to compute what is the error for an individual sample, and whenever I face an error, I am trying to modify the weight vector. So, you can say it is the pth sample where p is variable. Okay. So, this is what I have for an individual sample. Okay. So, a training sample which is fed to the neural network input, I know what is the target output, that is lowercase d, I know what is the output that I am actually getting, that is capital D. Difference between these two, my error. Okay. So, the weight updation rule in this case, unlike in case of perceptron criteria, where the weight updation rule was this, over here the weight updation rule is w k plus 1 is equal to w k minus eta times d, sorry, this will be the ith component, because I am talking about the ith component w only. W I k plus 1 is equal to w I k minus eta d minus d into x I, where x I is the ith component. Is that okay? So, this is what I have in case of a single output single layer perceptron. Okay. Where this Wi actually represents the connection weight from the ith component x I. So, this is my Wi. So, for every individual component I am doing it, right. And this single output neuron perceptron actually takes care of only two class problem. Okay. If the output becomes 1, I will say that the sample belongs to one class. If the output becomes 0, I will say the sample belongs to another class. Okay. But if I have multiple class problem, then this single output neuron model is not sufficient. I have to have a neural network having multiple number of outputs. Okay. So, I have one input layer where I feed in the feature vectors, okay, and I have an output layer where the neurons in the output layer are same as the number of classes that I have. Okay. The inputs are the feature components are fed to input layer, okay, which is simply passed to the output of the neural of the input layer neurons. Okay. So, these are my, say this is 1, then x 1, x 2, say this is x I, then I have this x m. Okay. I have the connections from outputs of each of the input layer neuron to the input of every neuron of the output layer. So, I have connections like this. Okay. So, it continues like this, and these are my outputs. Okay. So, I represent the connection weights as Wij. So, this Wij connection weight means that this is the weight of the connection from the ith node of the input layer to the jth node of the output layer. Okay. So, this Wij, this represents, say this may be my ith node of the input layer, and this is the jth node in the output layer. So, this connection weight from the ith node of the input layer to the jth node of the output layer, this is represented by Wij. Okay. So, accordingly, you find that if this output I say Yj, okay. So, this Yj will be nothing but, so this is Yj, summation of Wij x I varying from 1 to or 0 to capital M, okay. Then the non-linearity which is applied at the output of the output layer nodes. Okay. So, for different values of I, the individual components are being weighted by the corresponding Wij. Okay. So, at the output layer what I get is Wij into Xi. Okay. This also includes the bias, because I have started for I equal to 0 to capital M. So, I equal to 0 means this W0j, this connection component will actually correspond to the bias or bias weight. Okay. So, I have this Yj, which is a nonlinear function of sum of Wij into Xi, where I varies from 0 to capital M. Okay. In some cases, as we said earlier, that this non-linearity can be a threshold function. In other cases, the non-linearity can also be a sigmoidal function. Okay. Where the sigmoidal function is
Well, here input in node is only single. It may be multiple input, like in last case.
pardon?
In first column of nodes.
Yeah.
Yeah, why there is single input is there? In previous case we have multiple input are there.
No. You are talking about this one. Here, this is my say actually each of these are actually nodes, because when I am feeding this input, where do I feed? Okay. These are actually nodes which are unity gain nodes. That means, whatever is fed to the input, that is simply passed to the output. Okay. When I say the number of layers, this input layer is not really specified, because this comes by default.
So single input is to input to this nodes.
Input to these nodes. Okay. Here I said that this is single layer, single output neural network. When I say single layer, apart from this input layer, how many layers I have? So, that is only one. Here also it is single layer. Here also it is single layer. I have only the output layer. Okay. Input layer comes by default. It is simply where do I hook in the inputs. Okay. So, whatever input you are feeding here, the same input is simply passed to the output. Okay. And when these are connected to the inputs of the output layer nodes, every such input or output of the input layer node, that gets weighted by the corresponding connection weight, right. So, accordingly, the input to each of the output layer nodes, that is input to the jth output layer node, is this. The sum of w I j x I can consider that this is the input to the jth output layer node, okay. Or this node I can break actually in two parts. Every output layer node I can break into two parts. One portion computes the summation and the other portion gives you the non-linearity, that is f. Okay. Coming to our initial nodes which we have defined. Okay. I have an adder unit followed by a non-linearity, right. So, I can say that each of these nodes actually are broken into two parts. One part computes the summation, which is this, okay, followed by non-linearity f.
Sir, here layer word. So what it makes sense we are giving weightage. That is layering or
No, that is not layering. Multiple layers I will come later on. Okay. So, okay, because this question has come, let me just clarify this. See, what we have done in case of this single layer single output neural network. I get a linear equation of this form. This linear equation is equation of a single state line. Is that okay? If the point when it is greater than 0 means a point which lies on the positive side of the state line, which is given by this equation. If it is less than 0 means the point which belongs to the negative side of the state line given by this equation. So, this single layer single output neural network actually divides the feature space into two half planes. One half is positive, the other half is negative. Okay. Extending that to this single layer multiple output neural network, you find that each of these output neurons actually defines equation of a state line, is it not? Because this w I j into x I varying from 0 to m, for a particular value of j, it gives me equation of one state line, right. For another value of j, it gives me equation of another state line, right. So, when I have say on this output layer, if I have a C class problem I will have C number of output layer nodes, every node corresponding to one class, right. So, when I have this C number of output layer nodes, each of the nodes define equation of a state line, right, or each of them give you a linear equation, which is the discriminant function for individual classes. For classification, I will come later on. What I will do is, I will find out that for a given input, which of these output layer nodes gives you the maximum output, right. And the sample will be classified to that particular class which gives you the maximum output, which is nothing but the discriminant function that we have said in our earlier cases. Okay. And coming to our linear separability, because each of them are actually representing your linear equations. Okay. So, it is assumed that the classes are linearly separable. What you do if the classes are not linearly separable? Then this single layer will not be sufficient. I have to go for multiple layers. So, when I go for multiple layers, what I get is a nonlinear boundary is actually broken into linear pieces. So, piecewise linear approximation of nonlinear boundaries. Okay. So, I will come to that later on. Let us stop here today.